So, hello everyone, and a very warm welcome to you all to this webinar from IDEEMATEC in association with IDEEMATEC. I'm Ben Willis. I'm the managing editor of IDEEMATEC. Today we're going to explore some of the latest advances in tracker engineering, exemplified by IDEEMATEC's Horizon LTEC 1P solution. In a comparatively short space of time, single-axis trackers have become an almost universal feature of utility-scale PV power plants. This is partly because the additional cost of a tracker is more than outweighed by the fact that it enables local irradiance conditions to be exploited to the full, greatly improving project economics. But the growing sophistication of tracker engineering has also made them an indispensable building block in the overall resilience of PV systems, which are being exposed to increasingly extreme weather conditions. This is a consequence of the greater diversity of climates in which tracker-based PV systems are being deployed, but also a challenge more broadly as the deepening impact of climate change create more volatile operating conditions. Wind, in particular, presents one of the most significant structural integrity challenges PV systems face, and trackers as well. Ensuring the long-term reliability and stability of trackers during high wind events is a top concern for solar site owners, project developers, and EPC contractors. Designing a tracker to be structurally reliable for both static and dynamic wind effects is a key challenge for tracker manufacturers, and many different engineering approaches are taken to address wind and its potentially damaging effects. IDEEMATEC's LTEC tracker offers industry-leading stability in high wind regions, courtesy of its top-class design and engineering and extensive ongoing testing. And today we're going to learn more about some of the key features that make the LTEC a top performer in high wind environments. To guide us through this part of today's webinar, I'm delighted to welcome two of the IDEEMATEC team, Marcus Sonnleitner, Vice President of Product Engineering, and Victor Criado, Head of Tracker Simulation. We're also going to take a closer look at the testing to which the LTEC has been subjected, the all-important part of the process that proves a tracker can operate in the conditions it is claimed to be able to withstand. In the case of the LTEC, the tracker has proven its stability in a wind tunnel under wind speeds of 400 kph, and Parsa Enshai, Senior Engineer at CPP Wind Engineering, will talk us through the testing the LTEC has undergone and how this has helped refine the tracker's resilient design. After the presentations, we'll open the floor to questions from you, our audience. As always, this interaction is really important to us and to the webinar, so please put your questions for today's speakers in the questions tab on the right-hand side of your screen, and we'll do our best to answer them in the Q&A session after the presentations. But for now, without further ado, I'd like to hand over to our first speaker today, IDEEMATEC's Marcus Sonnleitner. Marcus, over to you.
Thank you, Ben, for the introduction. So, welcome everybody to the webinar, The Power of Stability Solar Tracker Design in High Wind Regions. Thanks that you joined for this exciting webinar. My name is Marcus Sonnleitner. I'm the Vice President of Product Engineering at IDEEMATEC. What is expecting you in the next following hour? Who we are at IDEEMATEC. We will show you what are design criteria for high wind regions, how we achieve them with design principles and methods, what are there for characteristics of still solar trackers, what we observed during our continuous testing and engineering. Why is it very important that we have advanced aeroelastic wind tunnel testing together with our engineering partner, CPP. And in the end, we are happy to answer your questions and answers, to answer your questions. Okay, let's go. So, IDEEMATEC, who we are. We are founded in 2003. Our headquarters is located in Germany, nearby Munich in the eastern Bavaria, in a nice area. We are pioneers in solar tracking, as we follow always a flat stove strategy and a decoupled drive since the early beginning. In the meanwhile, we are grown now to over 120 employees worldwide, have offices located over the globe in USA, Spain, and South Africa, for example, and we have total delivered more than 6 gigawatt of solar tracking solutions. Here, for example, one of our 2P solutions where we have installed 800 megawatt in Qatar. Here, a 1P tracking solution installed and commissioned in South Africa. We are also involved in 2P agri solutions in a research project in Austria. And here, one of our biggest achievements with the LTEC 1P, our 640 megawatt project in USA, Texas. Before we start with the engineering deep dive, let's have a short look on our one-in-portrait tracking solution, the LTEC 1P, and what are the main parts. So as we can build very long trackers, our design philosophy is that we use a string-sized table design. So this means one table consists of one string. We place, with the decoupled drive, we place the tracker, the drive unit consisting of an e-motor and a gearbox in the middle of the tracker. And therefore, the torque from the gearbox rotates the decoupled drive. The torque is transmitted to our power lock sprocket, which therefore enables to make the PV panels following the sun. We have the main carrier as an essential part for torsional stiffness. On the main carrier, the panel supports are mounted to carry all the PV modules. We have Sigma-shaped steel posts. On the posts with sprocket, we use a Sigma 180 cross-section, and on the standard post, a Sigma 140. So now let's go to the design criteria for high wind region and what makes this LTEC 1P feasible to go for. Before we start, I want to ask you two questions. What do you expect? Will global wind speed and heavy windstorms increase in future? My answer is yes, because the climate change is appearing global, and no matter where we are or no matter where we go, this is affecting all of us. So I expect that the global wind speed and heavy windstorms will increase in future. And a second important point, or a second question which comes to my mind is, if you expect that the risk category, importance factors, or the code-based design wind speed for utility scale PV power plants will increase in future. I would say yes, because committees, stakeholders, engineers started already these discussions to increase risk category from 1 to 2, which leads to a reasonable higher design wind speed for PV power plants. So this brings us definitely to the need that tracking solutions need to be ready for high wind regions. In order to achieve this, what is needed to be successful in high wind regions? You need a reliable and stable solar tracker design. You should use a flat stove strategy to secure the PV modules. You should have high aeroelastic stability using a multi-locking system. You should have increased stiffness and mechanical strength in the entire tracker using stiff posts, for example, or a high torsional stiffness on the main carrier. Of course, you should follow structural design according to national regulations, codes, local wind, snow, and seismic loads. Also here, site-specific wind studies, which are also offered by CPP, can give you in high wind region a better description of the wind loads. What else is needed? You should know where is the limit of your structure. You should apply advanced mechanical testing and use detailed FEM simulation to go into high wind region, because the structure is ultimate loaded. So you need to know where is the limit. You need to validate your design until it fails. You need to, and you should validate also simulation models. You should use a detailed and advanced wind monitoring coupled in the tracker control system. You should provide AC and DC solutions. You should also use advanced wind tunnel testing, where you get pressure coefficients and dynamic amplification factors. And very important is, from my point of view, that you have aeroelastic design testing. You should have aeroelastic wind tunnel testing, where you cover essential mode shapes and test also for high wind speeds and different scenarios like high or low ground cover ratios. In addition to that, the foundation design, which transfers all the load from the tracker to the soil, is also very important. And also you should have a proper pull-out test campaign. This point gains more importance in the last period of time, what I have observed. Also certifications like IEC, UL, and bankability reports are needed to demonstrate that the design, what you do, are state-of-the-art and reliable in front of investors, insurances, and stakeholders. So let's see how we can achieve this. At IDEEMATEC LTEC 1P, as I said, we are pioneers with the decoupled drive and the flat stow strategy. We have this since the early beginning, how we develop trackers. And we have three key differentiators. As I said, the decoupled drive, the permanent locking, and the flat stow strategy. Now, why are they important now for high wind regions? Let's have a closer look on them. First of all, the decoupled drive, what you can see here on the picture with the drive transmission and the power lock sprocket. The main benefits of the decoupled drive are already known. We can minimize civil works. We can go into slope tolerances in north-south direction of 20 degrees, which is quite high. And as all PV modules in one string have the same tilt, we have no string mismatch losses. And an extra benefit for high wind region is that with our configurable tracker design allows us to modify the number of locking points according to the wind load. As I said in the beginning, our tracker has a string-sized table design. So we design one table, it means one string, place them over the terrain, place the drive unit in the middle, and install the decoupled drive. When we have high slopes, we just add a Cardanian joint in the decoupled drive, and that's it. When we have high wind loads, we can modify the locking points, adjust span distances, or increase stiffness of the parts to achieve this. So the second important point is the locking technology. And I show you what benefit, how the working principle and what benefit brings this to high wind region. As I said, with our locking technology, the main goal or the main task of the sprocket is to transfer the torque from the drive transmission to the main carrier to track the sun, that the main carrier can rotate and follow the sun. But on the other hand, one essential task of the sprocket is to lock the tracker that it doesn't go unstable. And we can do this as often as it is needed over the entire tracker. What's the working principle behind this? Let's have a close look at the drive tube. So with the two pins, when they are rotated each 180 degrees, they are in a locked position. This means the wind load cannot rotate the drive shaft and make the tracker unstable. You can see here, for example, when we apply a reaction moment on the main carrier, it is impossible to rotate it. The tracker is locked. In more detail, what I just said is the moment the wind load generates a reaction moment on the power lock sprocket. And with the load transmission, we have a reaction force from the sprocket tooth to the two pins. And this force now wants to rotate the drive shaft and make the tracker go unstable. But when the pins are in a 0-degree position, it is impossible because the reaction moment is 0 Newton meters. When we rotate the tracker to follow the sun, we will have definitely different positions, for example, 90-degree. But here, we make sure with our structural design and the drive and the design of the gearbox that the moment from the drive is always higher than the moment of reaction when we want to rotate the tracker. When we reach the other 180 degrees, again, the system is locked. So with our patented locking technology, each 180 degrees of rotation of the drive shaft, the system is locked. And therefore, we can say no to torsional galloping, which is a huge benefit when we want to enter high wind region. And remember, we can install this as often as it is needed. Good. The last point, and one of the most important points. Remember, we come from the decoupled drive, the locking technology, and now we should have a flat stow strategy. And here we need to have a closer look on. So in a design wind speed event, we stow flat. Why do we do that? Because we need to secure the panels. The panels are the most expensive parts. They are much more expensive than the tracker itself. And in a design wind speed event, we just need to make sure that the wind load on the panel doesn't create failures, cracks, or other stuff, cracks on the panels. Therefore, in high wind regions, it makes sense that the load on the panels increases. But what is the solution is to go flat to decrease the load. But also there is a limit, yeah? Let's have a closer look. On the maximum wind pressure, for example, on a 615 watt module, on the y-axis, we see the module pressure. On the x-axis, we see the tilt angle of the tracker. Typical threshold values from module suppliers are 2,400 Pascal. And now, when we go into high wind regions, for example, USA, Texas, risk category 2, you see that the module pressure goes above the threshold when you maybe go higher than 10 degrees in the tilt angle. This means if you want to go into this region, you need to stow flat in the designed wind speed event. Otherwise, the modules fail. And at IDEEMATEC, we follow a nose down strategy with a 5-degree nose down. And this enables us in high wind regions that the panels are always safe. Now, what is crucial to know is that with a flat stow strategy, the torsional galloping or the aeroelastic stability is stiffness driven. So in order, if we now we have to increase our aeroelastic design, it does not make sense for us to install dampers. We need to install stiffness. We need to increase the stiffness of the tracker. And that's what we continuously test together with CPP in several tests, what we have carried out together. We obtain a typical W-shaped critical wind speed curve where we have a peak in a slight nose down position, which is typical for stiff solar trackers and a multi-log system. So this gives us a sweet spot here, yeah, which we can use to stow flat, to have high critical wind speed, and to go into high wind regions. We have tested several configurations at CPP, and also we have done the high wind speed test and a high row spacing test, and the flat stow strategy is validated. Now let's have a closer look on the high wind test, this 400 kilometers per hour. What was our idea behind this? Oops, sorry, wrong slide. Let's go here. What was our idea behind this? Our idea was to figure out what is the limit of the tracker. Yeah, how far can we go? What happens if we lock the maximum? And what you see is that torsional instability up to wind speeds is not observed. The tracker stays stable, but we see definitely a different vibration behavior as bending modes and other mode shapes appear. But torsional instability is not appearing. Now, let's have a closer look on a case study, what we have done for a project in Eastern Europe. With a design wind speed of 63.5 meters per second, 3-second gust at 10 meters height. For an outer area tracker, we use 2 locking points over one table. We make a short fixed span distance to have multiple to have their high torsional stiffness, and also a short fixed free span. In addition, the torsional stiffness of the main carrier has a medium grade, and the panel support we will use the long rails. In an inner area tracker, and this design was definitely we can go to one of our optimized design with a 5-1 configuration, which means 1 locking point, where the fixed free span is medium long, and the torsional stiffness of the main carrier is need to be slightly increased to be aeroelastic stable. What is remarkable here on this project was that the ground cover ratio was very high. This means the tracker rows were very narrow to each other, and in inner area, the sheltering effect was quite huge. If the row spacing, we did a separate investigation. If the row spacing would have been increased, trackers would be much, the distance between the trackers would be much wider. The solution would have been the best solution to use here 2 locking points. But you see, with our configurable design, we are always ready to apply a solution, and there is space left to go even higher. Good. Now, as a summary, the flat stow strategy is the only feasible solution for high wind regions. For us, it is not needed that we install dampers to be aeroelastic stable. With a flat stow strategy, we always have a high yield during a stow event, as the panels are flat and the sun always has a good angle on the PV module. The loads to the module's structures and foundations is reasonably low, which allows us to make a cost-effective design. And we have high natural frequency of the torsional modes to be aeroelastic stable and to avoid torsional galloping. So all this is needed to be successful in high wind regions. And now how we do this and how we achieve this, I will hand over now to Victor Criado, who will show you our advanced design principles and methods. Thank you.
So thank you very much, Marcus, and also thank you very much, Ben, for the introduction. So yeah, I'm Victor Criado, head of tracker simulation at the IDEEMATEC. And as Marcus says, I will explain the 2 next chapter, the design principles and methods, and also the characteristics of a stiff solar tracker. So I directly will start with the first chapter, the design principles and methods. And I want to start with a short introduction about these principles and methods in the design. So in order to achieve a solar tracker design for high wind region, it is necessary to use advanced mechanical testing and finite element method simulations. Regarding the advanced mechanical test, it's very useful, for example, to verify the performance of the structure according to different standards or different material limits. Also, it's very useful to analyze specific variables or parameters directly in the test. and also can be used to understand mechanical properties and behavior of some components under loading. Regarding the finite element methods, I want to say that simulation is a very powerful tool to analyze a wide range of physical phenomena that sometimes is not possible to directly analyze in the test, or the cost is quite high in the test, and also the time. Also, it's very useful to analyze complex details that sometimes is difficult to analyze in the test because it's inside other component, or it's very difficult to measure. So here it's sometimes a very useful tool for this kind of complex details. And I always say that needs to be validated. Finite element methods needs to be validated according experimental data to be sure that we are making a good simulation. Here we can see, for example, an example of a test and a simulation. And I want to say that the integration of these two methods leads to an advanced analysis of the trackers, and also that leads that the structure can be utilized to the maximum. So here I will start with explaining some of the tests and the simulation that we have done in IDEEMATEC. So I will start with the post-backlink test here in this slide. So the post-backlink test was analyzed with mechanical test and simulation. Here in the right, you can see the experimental setup of the test. And also you can compare it to the simulation model. Here we can see that the load it's applied in the same way. Also the boundary condition is in the same dimension, and also all the components and the full details of the components are modeled in the same way. For that test, we have do a validation, because always is need to do a validation. So we have measured the displacement in different areas of the test. You can see here in this image, and also we have compared the displacement to the displacement observed in the simulation. You can see that the displacement in the test and in the simulation looks that very good, and it's matching in the full range. So we can consider that this is a validated test. And also, when we observe the results here, we can see the test results, the post-backlink, and also the simulation, the post-backlink. We can observe that the area where appears the post-backlink is the same area in both in the simulation and the test. And also the load, the critical load, appears in a similar load level. So with this, we can say that this test is validated and we have quite accurate results. When we go to next example, also is the bearing test. Also the bearing test was analyzed with mechanical test and simulation. We can show the same, the experimental setup and the simulation model here, and we make with the same level of details. So we put the same components. We model all the details, content, and behavior of the real tracker in the simulation. And so here we also have analyzed when the bearing failed here. So when we analyze the test, we observe like a crack appears in a load of 32 kilonewtons. And looking to the simulation, we observe that the critical load in the bearing critical load appears at 28 kilonewtons in the same area. So this looks that after this critical load, the crack start to grow. So we saw that these two results are quite similar, and we considered it that good is a good similarities between the test and the simulation. And also this is so when we saw the contact area. So here in the right corner, we can see the contact area of the test after perform the test, and we can show the wear of some areas in the bearing. And when we observe the contact force in the same in the simulation, we can observe that we have the same contact area. This is because the level and the contact simulation is quite accurate here, and we consider that a good level in this simulation in terms of getting results for comparing to the test. Also, in the next slide, I will explain the next test. Is the peak-to-peak test. First of all, I want to say what is the peak-to-peak test. Is the maximum angle between upper and lower rotational deflection of the main carrier. This is useful to analyze and compare to the aeroelastic wind tunnel test, because in the aeroelastic wind tunnel test, as we can show here in this video, we have some deflection, and the idea is to analyze what is the maximum deflection that we can have in our tracker to validate the result from the wind tunnel test. So here we have done a mechanical test to obtain the maximum peak-to-peak angle. Also, we have done film simulation to validate the test, analyze different spans. And the objective is to demonstrate the maximum peak-to-peak angle that we can go with our tracker LTEC 1P. So for that, here we have done a test with this sketch. So we have placed a span length of our tracker. We have fixed one point, and we have placed a dynamometer to measure the load. And also we have placed two inclinometer to measure the rotational angle in the span. And we applied the rotation angle in the sprocket. Also, in the top, in the bottom corner, you can show a real picture from the test. Regarding the results of the peak-to-peak test, we saw that the main effect is the rotational deformation of the main carrier here, as we can show here. Also, there is a slight post bending in the post that we also analyze here in the test. There is a good correlation in rotational angle between test, FEM, and analytical results. So, for example, here you can check in this graph. This is the force versus the angle of the sprocket. The force versus the theoretical force is matching very well. So we saw that this is a quite good result from the test. Also, it's possible to check the stress and the strains directly in the FEM models. And yeah, when we validate the test with the simulation, we can check the maximum stress and strains in the simulation. And the last is that we have validated the 30 degrees peak to peak for all the spans in our tracker. So, okay, now I will explain another example of testing. It's the ball test. So the ball test is very useful to analyze the performance of the balls. First we normally analyze the maximum tip netting of torque of different balls. Here you can see in this graph or in this image that we have the torque versus the rotation angle of the ball, and we can show the linear behavior of the torque and analyze the maximum load that can transfer the bolt, and also we can analyze when the bolts start failing. Here, for example, you can see bolt failing at the end of the test. Also, it's possible to verify the maximum transferable shear force. We do it with this test, as we saw in the bottom of the image. So we put a fixed point, and also we have a pull force here, and we have the sample with the bolt with two plates in the middle of the test. Also, we measure the force, and the idea is to obtain the maximum shear force that can transfer this bolt. So this is useful to verify the maximum capacity of the bolt, and also to have a optimized and better design of the joints. Also, this leads to analyze different bolts, different coating of the bolts, and also analyze the friction in the test. Now, I will explain the last example of testing. This is the free vibration test. The free vibration test is carried out to determine the natural frequencies, aging modes, and damping ratios of our tracker. We have performed a test with different sensors. As you can see in this image, the acceleration sensors in the setup. You can see here, 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 and here. We test two configurations, and we perform a total of 31 measurements. Also here, you can see in the image the measurement model with the number of sensors that we place in the tracker. Also, we perform a FEM simulation with 3D simulation with cell elements, as you can see here in this image. And also, we include the effect of the ground stiffness in the simulation to be more accurate. Regarding the results, here I will show to you only the results for a configuration 9 post with 3 sprocket. And only 2 mode shapes. So first mode shape that I will explain is the vertical bending. Regarding vertical bending, we observe in the test and the simulation the same behavior of up-down of the main carrier in all the post distance between the post distance. And also we saw a quite accurate result between frequencies and simulation. When we compare the torsion mode shapes here in the same configuration with 9 posts at 3 sprocket, we saw also the same behavior of rotation between the fixed point or locking point between the sprocket. We saw a maximum rotational angle between also in the test and also in the simulation here. So also we observe a quite good accuracy in terms of number of frequency. So we can say that the natural frequencies was successfully measurement and evaluated. Results from measurement and simulation matching, so we can consider that this is validated. And also we observed a key point that the torsional mode shapes have an input in the post bending in the first torsional mode shapes. This can be observed here. So we not have a full torsion of the top structure. We also have some post bending, and this is one of the key points of the stiff solar trackers. With these results, I want to go and jump to the next chapter. The next chapter is the characteristics of a stiff solar tracker, where I will explain all these topics. So I will start directly with the post stiffness. So as we observe, in a stiff solar tracker, the top structure is more coupled to the post. So we don't have a full torsional mode shapes of the main carrier or torque tube. So we have a coupling mode. So post-bending effect appears in the torsional mode shapes. We have to consider that. And also high stiffness of the post is needed to to increase the stiffness of the global behavior of the tracker. So for that reason, we have compared different posts here, sigma post, W67 post, and C-channel profile post, to analyze the main parameters or the main parameters of stiffness of the post. Here I place the comparison of the sigma post to the W67 post. So when we compare sigma 180 per 100 with 3 millimeters to a W67, we saw that the mass is 6% lower in the sigma post, and also we have a bending resistance in the strong axis, 4% higher, and in the weak axis 37% higher. So also we observe when we compare to a C channel, we observe a same trend in the results, that the mass is lower in the sigma post, and we have a higher bending resistance and a higher bending in a strong and weak axis in the sigma post. So to fulfill all the requirement to have a stiff post in high wind regions, IDEEMATEC use sigma safe steel post because it have the higher stiffness profile, higher profile. So now the next slide is I will explain configurable table design, and I will show to you some mode shapes of different configurable tracker design. So I want to say that the LTEC 1P is a tracker that can be configured for different projects depending on the loads, and we can configure it to higher loads also depending on the strings, module, geometry. So this is very good that we can configure it out, but we have to determine properly what are the mode shapes and how is the influence in the stiffness. So first of all, I want to say the typical configuration, the 6.2, with a frequency of 2.83 Hz in exterior area. So this is a normal or a standard configuration that we use for external area. And also we can use the same configuration for inner area, but we can adapt the stiffness of the components to make it properly to the interior area. Also, another typical configuration is the 5.2 for exterior, as also Marcus introduced before. So we have a same behavior in the first mode shapes, as you can observe here. And normally also in the interior area, we can go with a 5.1 configuration. So it's one locking point in the middle of the span, and we have two free spans. So this is the minimum number of sprockets that we can place in one string. So with this, we can also optimize the inner area trackers. And also the last configuration that I want to show to you is the maximum configuration, that is to place one sprocket or one locking point in all the posts. And you can show here that with this, we will increase the frequency to 3.9 Hz. So this is a huge frequencies. And also you can observe that the torsional mode is coupled with the post bending. But with these results, I want to say that LTEC 1P is configurable to all the extreme wind regions, because we can make more stiff tracker when we need to go to higher wind regions. Now I want to share with you some mode shapes comparison of the trackers. So the idea is to compare the first torsional mode shapes in the tracker to different configurations here. So the idea, first of all, is that the first torsional mode shapes is the most critical to determine the stability of the tracker. So the main idea of this slide is compare the result from LTEC 1P to other trackers, like conventional tracker with one fixed point in the main carrier or in the torque tube and have a long span, and also to compare to other multi-block trackers blocking the system in the top of the structure. So first of all, I will show the results from the LTEC 1P. So with the real pulse stiffness, you can show here that we have a frequency of 2.73 Hz in the LTEC 1P. But when we make a rigid pulse, so when we make the pulse with infinitive stiffness, we observe that the frequency increase a lot. So this is one of the main reasons that the first torsional mode shapes have a huge influence in the pulse bending have a huge influence in the torsional mode shapes. When we compare this in a conventional tracker with one blocking points in the mid of the total span, we can observe that the frequencies drop a lot because we have a longer span here. And also when we compare it to conventional tracker with rigid pulse, we saw that the influence of the rigid pulse is less than comparison to a LTEC 1P, but also is not negligible. We can observe when we compare to conventional tracker with rigid pulse, the frequency increase. Also, when we compare with multi-block trackers blocking the top of the structure, we observe that frequencies also again is higher than the conventional tracker, and the behavior is quite similar to LTEC 1P. And also, when we observe to rigid post, the comparison, we observe that there is a huge increase to the from multi-block tracker to rigid post. So remember, no post in any tracker is rigid. Always have an influence. So bending stiffness of posts have an influence in the first torsional mode, as we observe here. And also, post stiffness have to be modeled in the wind tunnel test. So the key takeaways that I want to share with you is that design components for high wind region requires to use advanced simulation techniques combined with extensive experimental tests to achieve an optimal and reliable design. Accurately modeling of the pulse is crucial in wind tunnel tests for multi-block systems, and the mode shapes of stiff solar trackers are more complex with the influence of the pulse bending, making advanced 3D aeroelastic wind tunnel testing necessary for stability of the tracker. With this slide, I would like to hand over to Parsa for explaining this topic, the advanced 3D aeroelastic wind tunnel test. So I will hand over to Parsa.
Thank you. Great presentation so far, Marcus and Victor, and thank you for the introductions at the start, Ben. As Ben mentioned at the start, I'm one of the engineers at CPP, and today I'll be talking about the ongoing collaboration between CPP and the Advanced Wind and IDEEMATEC and the Advanced Wind Tunnel testing that we've done over the last few years, and generally go a little bit further into the topic of aeroelastic and stability testing. So just a bit of background on who we are. CPP, or Cermaq Peterka Peterson, is a group of experts mixing aerodynamics and structural engineering. We've got offices around the world, in Australia, where I'm located, Canada, Malaysia, and the US, and we've got 4 boundary layer wind tunnels, 2 in the US, 1 in Australia, 1 in Malaysia. But we don't just have experimental capabilities, we also have computational capabilities to complement those. And really our bread and butter, and I guess our history, has really been focused on the structures that you can see in the pictures on the right. So that's tall buildings, stadiums, and cool structures like the Sydney Opera House. But over the last decade, we've really focused on the solar services that's really the focus of this discussion today. Now, the main two aims of the solar services that I'm talking about are to offer a package of studies that assist a tracker designer to then evaluate the design, and so it's optimized and cost effective, but more importantly, understand the risk from wind-induced effects and understanding the probability of failure due to wind-driven events. And when I talk about these risks, it's probably easiest to show some pictures that I'm sure you've seen all over social media. So these are your instability-driven failures. They could be your panel failures, post failures, or any sort of cool dynamic effect that's happening, or maybe back to panel failures here. Now, we've got a range of services, and if we were to take a rough high-level view of going from a product design all the way to building a site, we can get involved with different players in this process. So that's whether that's your product vendor, like IDEEMATEC, an EPC, or an owner-operator, to again go back to those two goals of trying to optimize the system, but really understand the risk associated with wind-related events. Now, the focus of today is really on the product side, so that's wind tunnel testing. That's generally where you would start, and in particular, we're going to talk about aeroelastic instability testing. Now, again, torsional instability is probably easiest explained with a video. So here you've got the far half tracker in this video failing, and then that leads to a cascading effect where the other parts of the tracker fail, and then that goes further downstreams into the other rows. Now, obviously this is quite cool to see as a wind engineer, and it may be exciting to figure out, but it's not something you want to see as a tracker designer or as an owner or operator in that case. So really, the idea here is to avoid these type of risks, and it's really important to understand that this kind of instability is a catastrophic failure. So it should really be designed up to that ultimate strength wind speeds. Now, how do we address that, and how do we study it? So you could go back, and this is a great place to start, which is 2D sectional models. This is really coming from bridge aerodynamics and understanding the effects of flow, solid interactions. Now, for such a flexible system like a solar tracker, there are a lot of assumptions that need to be made to squeeze this three-dimensional structure or three-dimensional interaction down to a 2D model. So there are a lot of assumptions that are made in this process, and some of them are likely to be wrong along the way. So it's very difficult to kind of squeeze those properties down, and then it's also very difficult to model the correct approach flow for the wind due to the turbulence that's needed, due to that boundary condition that's needed, and it's also difficult to model the flow as it interacts with multiple rows or as it comes in from different wind directions. So generally, this is a good place to start. And this is also where CPB started investigating these about a decade ago. But now it's really moved on to three-dimensional models. So now, if you're going back to this 3D idea and you're mostly interested in torsional instability, you can take a tracker and you scale its geometry to start with. That could be somewhere between 1 to 20, 1 to 40. You scale velocity, that's the wind speed that you're running in the tunnel and what it's equivalent to in full scale. And again, if you're focused on the torsional component of the structure, whoops, skipped a slide, you would then be modeling its structural properties that are associated with torsion. So that's your torsional stiffness, that's your mass moment of inertia, and the torsional damping. And once you put it in the tunnel, it would look something like, let me go back to this video, like this video, where you have sections of the tracker at the end, whether it's a single drive system twisting, or if it's a multi-drive, then twisting between the two drives. As Victor mentioned though, in cases where you have a multi-drive system, and this is really a play between the stiffness in torsion and the post stiffness, they could end up coupling. So in cases where you need to also model the post stiffness, then you need to include these additional properties like the bending stiffness of the post, the mass of the tracker deck, as well as any kind of unique properties to a system like their sprockets in the case of IDEEMATEC. So you then have modes like these, as Victor just showed before, that also need to be modeled in the tunnel themselves too. So you could have a mode that's twisting the entire tracker due to post bending or sections of the tracker, and those need to be modeled in this case too. Great, so you've got your model and it's acting like the full scale structure. So now it's put into the wind tunnel, and there are 4 things to be looking out for here. First of all, the flow that's going to approach the model. So in general, these structures are built around in open fields. So you'd be looking at, not sure what's happening with the screen, in an open country approach. So that would be your exposure C in American standards, or terrain category 2 in Australian standards, and so on in different codes. So that's correctly modeled with the upstream fetch that's existing in the tunnel with different mechanisms. You then make sure that you have these multiple rows so that you can capture those aerodynamic effects that or the flow field that I was referring to with these multi-rows. You need to make sure that the flow that's approaching and interacting with these models is accurately measured. So you have wind speed measurement locations, and you also need to understand what the directionality of wind will do to the structure and what the interaction will be like. So generally, these would be on an automated turntable that can then test different wind directions. And once that's all there, you can test it. So this would be testing the trackers at whatever tilt is of interest. So in this case, on the left, you have trackers testing upturn stability at 0 degree tilt. And you can see that it's not quite that torsion-only model anymore, and actually more like trackers dancing in the wind. Do the same thing and test the trackers at other tilts, in this case, looking at 30 degrees. And the interaction is different, and the instability is different. Now, the output of the studies would then be an understanding of the instability speeds that you would expect at different tilts. So a typical or very generic curve here for a low damping system will look like the W shape that Marcus was referring to earlier. And you would, for example, have your tilt on the x-axis against those wind speeds at each of those tilts. Now, there are 2 key pieces of information to extract from a plot like this. That's the lowest wind speed. So you have to make sure that you are, no matter what your operational tilts are, you have to be in a stow position before you reach that wind speed. And the wind speed that each, or the best stow tilt can reach. So whether that's 5 degrees, then the maximum wind speed that can reach, and that sets the design wind speed that it should be compared to in full scale. Now, if you were to adjust these results, there are 2 main approaches that are taken. One could be increasing damping, and that really has a major effect at the moderate to high tilts, where you would have significant improvement and you would end up with a slightly different shaped curve. Or you could also go down the IDEEMATEC approach, which is increasing stiffness of the structure, and that has a general improvement across all tilts. Now, how do you do those 2? Increasing stiffness, as is the case for the IDEEMATEC configuration 5.5 here, is through thicker torque tubes, larger torque tubes, or introducing more drives to the system so that you have shorter spans and higher torsional stiffness. And as you can see, this can reach immense speeds, whilst a different approach would be to increase that damping, and again, that has a much more of an effect at tilts away from 0. But in general, there are many different solutions, and really the idea is to make sure that a test is done specific to a particular configuration, whether that's the configuration of the system or the array configuration. And I'll just finish off around here, which is really going back to that initial message of trying to understand risk and probability, and that's coming through different product services, but also site-specific services. So we've worked with IDEEMATEC over the last 3 to 4 years, and really have an ongoing process where it's potentially including aeroelastic testing for multiple configurations, as well as screenings and this ongoing expert consulting to then understand how these product testing and how that risk is then applied in full scale at different sites. Thank you very much. Be happy to answer any questions.
Thank you very much, Parsa. Concluding a fantastic trio of presentations there. So thanks all for those. Some really great insights, very good detail, and very interesting. So thank you. We've got a few minutes left on the clock just to rattle through some questions. So there's one which actually has two, which I'm going to put together regarding the flat stow strategy. So first part of the question, how does wind directionality affect a tracker's flat stow strategy? And also in areas such as Texas, where you mentioned one of your projects at the outset, Marcus, where there is a high risk of hail, what the approach there would be, whether you'd still opt for a flat stow approach or whether an at tilt stow option would be preferable for hail events. So a couple of questions about stow there for you.
Yeah, thanks for raising the questions from the audience. So in terms of high hail risk scenarios, we use the advanced Tor stow hail strategy, where we can stow in a high tilt angle, 70 degrees, in parallel with an increased working speed of the tracker. In order to cover the wind directionality, we also use wind direction sensors, and in case the wind direction changes during a wind event, we use the time frame when the winds are coming mainly from north or south direction to rotate the tracker from one flat stow position to the others. So also this is then not a problem.
Great, thank you very much. And in terms of certifications for high wind regions, I mean, obviously we've heard quite a lot about the sort of rigorous testing that you've put your trackers through, but in terms of certifications for high wind regions, I wonder if you could give us some thoughts on that and how important that is for trackers such as yours.
Yeah, it is very important that you have the certifications like the bankability report, IEC testing, UL testing, and you must make sure that this is always state of the art to update them frequently in order to have the documents ready for stakeholders, investors, and insurances.
Great, thanks very much. Sorry.
Maybe, okay. Yeah, in addition, I want to say that the certifications are used as a benchmark to compare tracker designs, as there is not yet the full overall existing guideline available on the market, the handbook of solar tracker design. So that's why the certifications are highly needed.
There's an interesting question here, which I guess probably for you, Marcus. It's about again testing. So the question is: given the 2,400 PA industry standard module pressure rating, would it be fair to say modules themselves are likely to fail in high wind conditions before your tracker locking system?
Well, in the end, with the flat stow strategy, we try to save the panel. This is the main task of the tracker. One of the main tasks. The one is to follow the sun, and the other one is to save the panels in the high wind event. And only with the flat stow strategy, you can achieve pressure values on the modules below threshold values. So for me, there is no other way to go to make this.
Great. Thank you. Understood. Question for Victor. What is the maximum wind speed you've considered in a project?
Yeah, thanks, Ben. So yeah, actually we have a project in an island in the Andean Ocean with a maximum width speed or design width speed of 71.2 meters second, 3-second gust at 10 meters height. So this is a quite huge wind speed that we are currently working, and with our locking system, we can have a good solution for these high wind regions, of course.
Thanks. And in terms of the testing, which of the experimental tests do you consider most important for high wind regions?
Okay, I think from high wind regions, I consider the free vibration test, and to get accurately the mode saves, including the post-bending effect. This is very important to have a good mode saves that can be used in the 3D wind tunnel test. Also to test the peak-to-peak test to know the maximum capacity of our rotational angle, and also validate the wind tunnel test, and also to determine what is the maximum load of all the parts of the tracker, like a post with post backlink test. Also the main carrier, we have to determine the maximum capacity, the bearing. So we have to determine the maximum and test until the maximum these components.
Thank you very much. And in terms of validation of the aeroelastic wind tunnel testing, which you put your trackers through, how is that done? How do you validate the testing that you do?
So mainly we have used the peak-to-peak test, this test that we determine what is the maximum rotation angle that can have our tracker. So we measure and we validate it with FEM simulation, and also we follow a research paper to analyze in detail all the maximum capacity of our tracker. And with the results from this test, we can validate what is the maximum angle that we can use in the wind tunnel test, and the aeroelastic wind tunnel test, and use properly the result from the wind tunnel test in accordance with the maximum rotation angle from testing in the LTEC 1P.
Thank you. And a couple of questions about the testing for Parser here. So what stage does CPP get involved in the development of the trackers, and how long does a wind tunnel test? How long does wind tunnel testing typically take?
Yeah, that's a good question. So we, as I said at the start, there's a bit of a process in terms of going from product design all the way out to building site, and maybe even going through failures and trying to investigate those. So we really get involved at all stages. But obviously, as a product vendor, we recommend the earlier on the better, so that we can provide some inputs into that structural design. The wind tunnel tests, or any sort of wind tunnel services, would then take, depending on what type of services, could be from a month to a few days to a whole process. But we usually get involved with our clients for years to go through this long-term collaboration, so that we kind of walk them through and work alongside them for years.
And is a new test needed for each site, or is it a sort of kind of one size fits all thing?
Yeah. So if you are building the same product over and over again, which I don't believe really any product vendors are, then yes, you could use the results from the same product. But what's also very important on the other end is that every climate is different that you're going to build in. So it's really important to understand, again, the combination of that site-specific climate and the product itself. So one test could help with a lot of sites, but really understanding the full scale site risks is per site.
Great stuff. Thank you, Parser. So we've got a few quite detailed technical questions that have come in. I'm very sorry to say we're out of time now, so I'm going to have to leave those, because we've come to the end of our allotted time now. But after the webinar, recordings of the presentations and the slides you've seen today will be emailed out to webinar participants in the next few days, and also be available on PBTech. And as far as I know, contact details for today's speakers will be on those materials. So for those who put in questions but I've not had a chance to get to, you by all means can follow up with our speakers after the event. So yes, that brings us to the end of the webinar. So thank you very much for tuning in. I know I found it very insightful and stimulating. So thanks again to our presenters today. And yes, a huge thanks to IDEEMATEC for sponsoring the webinar, and to Parsa from CPP for your involvement too. Thanks to everyone for tuning in. I hope you can all carry on the conversation after this event. And that's all from us today. So goodbye from me and all the team at PBTech. Have a very good rest of your day. Thank you very much.